Hi Bobcats! In this video we're going to take a look at quantum numbers. Our objective is to be able to analyze a given set of quantum numbers to determine if that particular set of quantum numbers is allowed or not. Quantum numbers are a bookkeeping device that we use to keep track of the infinite number of solutions that exist to the Schrödinger equation. It's just a way of bookkeeping. And we have four quantum numbers. There's the principal quantum number, which is abbreviated N. I'll go ahead and circle that down here so you can see where I'm talking. The principal quantum number N. We also have something known as the angular momentum quantum number, L. Some textbooks call that the azimuthal quantum number. We also have the magnetic quantum number, M sub L, and the spin quantum number, M sub S. So what do these things mean? That principal quantum number is associated with the energy level of the orbital. So if the principal quantum number is 2, it means that we're in the second energy level or the second shell. The values that the principal quantum number can take, which is this middle column right here for the values, the smallest number that N can take is 1, and then it just counts up by the counting numbers. I put 7 in here because 7 is the highest value for the principal quantum number that real atoms in the periodic table use. In theory, and with all of the work that physicists are doing with particle accelerators, if they keep inventing new elements, that number can continue going up, but currently real atoms only go up through 7. The angular momentum quantum number can have as its smallest possible value 0, and as its largest possible value 1 less than the principal quantum number for that particular orbital. And we're going to associate with the angular momentum quantum number which type of orbital we're talking about. Is it an s orbital, a p orbital, a d orbital, or an f orbital? And we'll look more closely at that on the next slide. The magnetic quantum number can be as small as negative L. So M sub L depends on L, and of course L depends on N, so it all works backwards. So the smallest value for M sub L is negative L, and then it counts up through 0 into positive numbers, and the maximum number that it can be is L. So let's say that our angular momentum quantum number is 2, then our magnetic quantum number could be negative 2, negative 1, 0, positive 1, or positive 2. Then our spin quantum number, M sub S, is either plus 1/2 or minus 1/2. That's probably the easiest one when we're analyzing quantum numbers because it has to be one of those two values, and that value is independent of the other 3 values. Now these first 3 values, N, L, and M sub L, describe an orbital, but M sub S describes the orientation of the electron in that orbital, and there are only 2 possible orientations. We'll call one spin up, that's the plus 1/2, or spin down, which is the minus 1/2. The table on this slide shows you the correlation between L and what type of subshell it is. If L has a value of 0, we're talking about an S subshell. If its value is 1, we're talking a P subshell, an L value of 2 is a D subshell, and an L value of 3 means we're looking at an F subshell. Let's take a look at helium. Helium has 2 electrons, and its electron configuration is given as 1s2. This is a sketch of the s orbital, so we should probably label this as 1s. This is indicating the 1s orbital, and there are 2 electrons stuck inside of there. We could also draw the orbital energy diagram. So we're showing the 1s label down below, and then 1 electron going up and 1 electron going down. So if we are going to describe this orbital, this number out in front, 1, that is our principal quantum number. So if we're looking at the values of n, l, m sub l, and m sub s, n for this orbital is 1. Now because it's an s orbital, the number for L is 0. And then m sub L depends on L. It ranges from negative L through positive L, but since L is 0, the only value m sub L can be in this case is 0. And then m sub S is either plus 1/2 or minus 1/2. So for that arrow that's pointing up, m sub S would be plus 1/2. And for the arrow that's pointing down, m sub S would be minus 1/2. So how are we going to interpret this? This full set of 4 quantum numbers, which on the first row was 1, 0, 0, plus 1/2, that describes an electron in the 1s orbital that's oriented spin up. Now, to complete the the quantum numbers for the second electron, I should fill in the 1, 0, 0 here, because these first 3 quantum numbers describe the 1s orbital, 1, 0, 0. And then this last quantum number of negative 1/2 describes that second electron, which is oriented spin down. So 3 of the numbers describe the orbital, and then the 4th describes the electron's orientation in that orbital. In a typical multiple choice quiz or test over this topic, you'll normally be given a set of 4 quantum numbers, and you'll be asked to determine which ones of these sets are allowed. You might be asked to correct it, so whatever is wrong, correct it, so that the set of numbers is allowed. So you just need to understand what the rules are for each one of these numbers. And remember that m sub L depends on L depends on N, and m sub S can only be plus 1/2 or minus 1/2. So if we're going to look at this first set of quantum numbers, 1, 2, -1, and 2, a couple things jump out at me right away. Probably the very first one that jumps out is m sub S. M sub S can only be plus 1/2 or minus 1/2. Any other value is not allowed. The next thing that jumps out at me is that L is too big. The largest value that L can take is n-1, so this would have to be 0. If L is 0, then m sub L runs from negative L through 0 to positive L, but since L is 0, the only thing m sub L could be is 0. So we could have 1, 0, 0 plus 1/2, or we could have 1, 0, 0 minus 1/2. For the second set of quantum numbers, n is 3 and L is 2. So that looks okay because the biggest that L could be is n-1, which is 2. It would also be allowed if L was either a 1 or a 0, but we've got 2 and that's good. M sub L runs from negative L through positive L, so if L is 2, M sub L could be -2, -1, 0, +1, or +2. So -2 is just fine. And then M sub S needs to be either plus 1/2 or minus 1/2, so that one's good. So it looks like the second set is an allowed set of quantum numbers. For the next row, 3, 3, 2, -1/2, it looks like the problem here lies with L. L has to be 1 smaller than N for its largest possible value. So this L would have to be 2, it could be 1, or it could be 0. I'm going to stick with just 2 because if we leave it at 2, then M sub L is okay because M sub L runs from negative L through positive L. So if L is 2, M sub L can be 2. And so if we have 3, 2, 2, -1/2, we're looking at a good set of quantum numbers. And then last but not least, that last set of quantum numbers is 2, 0, 1, -1/2. If N is 2, L could be 0 or 1, so having an L value of 0 is good. If L is 0, then the only thing M sub L could be is 0, so this one is not good, but if we corrected that to a 0, we would be okay. And then M sub m sub s is -1/2, which is a good value. In short, if you're going to analyze a set of quantum numbers to determine if they're allowed or not, you need to understand that n can be 1 at the smallest, and then it counts up with the counting numbers. L starts at 0 and counts up to n-1 for its maximum possible value. M sub L runs from -L through +L. Those three quantum numbers, n, L, and m sub L, describe an orbital. Then m sub s will describe the orientation of an electron in the orbital, either spin up or spin down, and so it can only be +1/2 or -1/2, and it is independent of n, L, and m sub L.